Good afternoon, boys and girls and ladies and gentlemen and everybody else who's here.
I do have an announcement.
We have an announcement. Okay.
Even though this is a PhD student presenting, the faculty do not need to fill out evaluation forms because it's not for a PhD presentation. Because I've just been asked twice, so I'm like, oh, just get that out there.
Thanks, Jane. I was going to say something about that.
Yeah.
But our speaker today is our very own PhD student, Gabrielle Quadrado. She's been working with Katie Seraphin. Yeah.
What's that?
She has a Bachelor of Science in Oceanography from the Federal University of Rio Grande. She has an MS in Geosciences from the Federal University of Rio Grande do Sul in Brazil. She's already published 2 papers based on those 2 theses. A little side note. This is actually a practice run for a talk that she's planning to give at the International Conference on Coastal Engineering in Sydney, Australia next month, coming right up. So when she asked if she could have some time, she said, sure, it'd be good practice. So it may not last the full 45 minutes because it is a 20-minute limited talk, right?
Yeah, I'm not quite sure because I did an extended version.
Okay.
I may get carried away.
So plenty of time for discussion at the end. And if you have any suggestions on how Gabriella might improve her talk for the international conference, then I'm sure she would be highly receptive to it. So the title's on the screen. Take it away, Gary.
Thank you, Dr. Binford, for the introduction. So hello, everyone. Today I'm presenting what drive extreme events, evaluating the major contributors to total water levels along the US Atlantic coast. So let's start with water levels. So on the coast, water levels are influenced by a combination of different hydrodynamic processes, which include geostatic and isostatic sea level, which is basically sea level rise related to sea level rise. We have astronomical tides, storm surge, sea level anomalies. So here's the influence of interannual and interdecadal climate oscillations over water levels, and waves. So combined, all of these processes, they determine what we call total water levels. So in my research, I'm evaluating the relative contribution of hydrodynamic processes to extreme total water levels along the US East Coast. But why does it matter? Why is this important? So understanding extreme total water level matters because, as you may all know, flooding and erosion are major coastal hazards worldwide. And they're not only affecting our coast here in the US. And while the magnitude of total water levels may dictate the potential for flooding and erosion, it's by understanding the relative contribution of these processes to total water levels that we can have insights on how changes to stormness, sea level rise, a wave climate, all in the context of global climate change, can affect our extreme water levels now and in the future. And all of this is important because if we understand exactly what is driving extremes and what are the effects of climate change in each of these processes, we can make better predictions and more robust estimates that can aid decisions and policy making, especially in the context of emergency and urban planning. So let's dive deeper on total water levels. So if we get a cross-chart section at a given beach, we can see that total water levels are basically the linear superposition of still water levels and wave run-up. So we're basically summing these 2 components. Wave run-up would be the maximum vertical extension of the wave-induced water level. And still water levels are going to be defined in a few moments. So in my research, still water levels are a measured amount, and wave run-up is defined as the 2% exceedance level for wave run-up, which is estimated with an empirical equation, which parameterizes this component as a function of deep water wave height, deep water wave length, and beach slope. Beach slope corresponds to the angle between the base of the dune, which is, this beach is kind of flooded, there's too much water here, but this would be the dune toe, the base of the dune, and would be the angle related to the shoreline. So this would be the beach slope we're using to estimate our wave run-up. Moving on to still water levels. Still water levels are composed by mean sea level, which in this research are defined as the long-term and the interannual variability. So we do not have only the isostatic and eustatic levels. We also have all of those sea level anomalies induced by climatic oscillations I mentioned earlier. So all of these is reflected on this component right here. You can also see that I have plots for all of the components. Then we have our astronomical tides, and we also have non-tidal residuals. So non-tidal residuals are further split into two other components. We have the intraannual seasonal signal, which is basically related to thermal expansion, or in the case of the southeast coast of the United States, we have the Gulf Stream, which has a kind of consistent position and it changes seasonally. So these may also be reflected within this component. And we also have the high frequency residual related to storm surge, which includes the effects of both wind setup and barometric pressure over water levels. So all combined, they generate total water levels. So my study area, as I mentioned earlier, is US Atlantic coast. So it goes from Florida, Georgia, the Carolinas, the Virginia, Maryland is not included, Delaware, and New Jersey. And I use three main data sets. So for waves, I'm using the global ocean waves reanalysis data set. And all of these circles right here, they represent where these hindcast nodes are located. I use water level time series, which are extracted from NOAA's site gauges. And I have this all according to the Greenwich Mean Time meters, according to the mean lower low water level, mean lower low water datum. And you can see the location of these gauges right here, represented by the triangles. And I also have a data set for beach slope. As I mentioned earlier, I use this to estimate my wave runoff, which is extracted from the USGS lidar-derived beach morphology. However, I averaged all of these local beach slopes, but I'm using here the median value across all stations because I want to isolate the effect of the hydrodynamic processes. I want to understand hydrodynamically what is driving extreme events. So I'm using a constant beach slope. Okay, moving on to the research questions. So there are two main things I'm trying to answer with this piece of research. First is what drives extreme total water levels on the United States Atlantic coast. And to do that, I will quantify the percentage each process contributes to total water level annual maximum events from 1980 to 2020. And the second part is extreme total water level events driven by extreme processes. So I do two basic things to answer that. I assess the co-occurrence of the component's annual maxima during the peak of the total water level. And then I also quantify the probability of the component's annual maxima happening at the peak of the total water level. So more specifically focusing on the methods, here we define extreme events based on an annual maximum method. So here we have a plot, in blue we have the total water level time series after I aggregated all of those components together, and the identification of all the annual maximum events for these 40-year time period. And if we zoom in into one of these annual maximum events, I picked the 99-1 event, which happened on Halloween. Not relevant, but here I have a plot with 20 days of data, and I have the elevation for each of these components. So now we're looking at what is exactly this event look like. So in black, I have total water levels annual maximum. I have in orange the mean sea level component. In purple, we have tides, astronomical tides. In yellow, seasonality. Green, storm surge, and here in blue we have wave runoff, and the red stars depict the exact moment when we had the peak of the annual maximum total water level. So one thing that stands out to me here, okay, we have wave runoff at their maximum during this 20 days period. We have the high tide during the peak of the total water level, but you may notice that the peak of the storm surge here in green is not exactly at the same moment where we are seeing the peak of the total water level. And what this tells us is that we do not have necessarily the most extreme processes driving the extreme total water levels or the annual maximum event at our coasts. So we're not experiencing worst case scenarios yet. but this could happen in the future. So this is how important it is to look at these components and understand how they're changing. So besides looking at the magnitude, as I mentioned earlier, I'm interested in looking at the relative contribution. So we can transform all of this into a percentage where you see the exact influence of each of these components to the NO maxima total water level. And once again, here with this analysis, we can identify the major contributors to extreme total water levels along the US Atlantic coast. And this helps us to contextualize current conditions and future changes. So on the next part of this research, I'm keeping this slide here. So to check if extreme total water levels are driven by extreme processes, we are identifying overlapping NO maxima between the NO maxima of the total water level and the NO maxima of the component. Are they happening in the same day or in the same period? So to do that, I define this time window of 3 days, which is the average storm length defined by many studies that focus on extremes. And I check if they're happening in the same time window. So if we go back to this Halloween extreme total water level, we can see that in this plot right here, I have in the y-axis the elevation of the storm surge. The black circles represent the storm surge during the total water level NO maxima, and the greens represent the storm surge during the storm surge NO maxima, which is not always the same. And this is what I'm trying to answer. So we can see that we have the NO maxima total water level here on October 21. Coincidentally, storm surge also happened on the same day, is slightly displaced in hours. So we say this event occurs. We can get another example right here. This one, we have the storm surge during the total water level NO maxima happening on April 14, and the storm surge during the storm surge NO maxima on April 17. 3 days of difference, they still co-occur. But we can also get another example, like in 1983, where the events, the NO maximum events, they occurred in time periods completely different. So I'm interested in looking if these events are occurring or not, because of the importance of understanding if worst case scenarios are frequently being experienced. I also quantify the probability of these events occurring or not. I fit a generalized extreme value distribution to the storm surge component, to the NO maxima storm surge, or to other components that I'm also looking at. So I fit this distribution to the components NO maxima, and we can go back to this event again, check the magnitude of this event, which is 0.52 meters. This is during the total water level NO maxima. We can find it where in this distribution is the storm surge located, and we can quantify the probability of this event happening, this type of storm surge, based on the distribution of storm surge NO maxima, not total level NO maxima. So with these, we can estimate, after feeding the distributions, we can estimate the return period, and we can see that this storm surge has of 0.52 meters has a return period of 1 year. So it has 100% chance that will happen in a year. So it's a very common event. It's not one of the most extreme storm surges that these place experiences. And we do this, we replicate this across all stations, and we estimate this return periods during total water level NO maxima for storm surge and wave height. So once again, here we can identify the likelihood of current maximum events, which help us to provide information on the potential for coastal zones to experience worst case scenarios, which I was talking earlier today. And worst case scenarios here are defined by the simultaneous occurrence of multiple drivers at their maxima. Okay, so let's start talking about results. Before I move on to extreme events, I want to talk briefly about total water level average conditions. So the conditions that happen when we go to a beautiful sunny day at the beach, and the typical total water levels that are happening on that day. So here I have a plot for all of the stations from Fernandina Beach, Florida to Sandy Hook in New Jersey. And here what I have is the average of all the total water level average conditions I evaluated for each of these components, for each of these locations. Same components here, mean sea level in orange, astronomical tides in purple, seasonality in yellow, and storm surge in green, which do not show too much. It's part of the results, and wave run-up in blue. So the main findings of looking at the average conditions is that we have tides and waves that are the major drivers of average conditions. So they are always important and always relevant in determining what is the total water level. So they contribute to approximately 97%, which is pretty much all of the total water level. In addition to that, we see that we don't see any green in this plot right here, which is storm surge. So the average contribution of storm surge, we can say, is negligible. These are average conditions. There are no storms there. Of course, it's a very small contribution. And this is intuitive, but it doesn't apply for all of the components. But here, the larger the tidal range, the larger the tidal contribution to total water levels. So tides are very important. So of course, they have a lot of implications over the magnitude. But you see in the next slide that we do not always have magnitude and relative contribution varying in an equal proportion. So we're increasing the magnitude and we also increase the relative contribution. This doesn't necessarily happen because we have other processes contributing to this total water level. So one component can offset its contribution to account for the increase in another one, which may not increase its contribution. So it's a complex system of all of these components interacting and contributing differently in different circumstances in terms of total water levels. So now we finally go to see what drives extremes, and we can take a look at the annual maximum events. So here I also have the average for all annual maximum events that were found for each of these 10 stations. And once again, we see that total water levels are mainly driven by waves and tides. So they are always important, but you can see that before they were contributing to 97%, in here they decreased their contribution to 88%. So tides are the process here that are decreasing their contribution. So they are not a driver of the extremes. They do contribute to it, but they are not the driver. The remaining components are contributing to approximately 12% of the annual maximum total water levels. And one thing that's very interesting is that when we think about extremes, we tend to think about storm surge, and we are right in thinking about that because the storms are what is elevating our water levels. But in this results here, we can see that storm surge is the third largest contributor, contributing to approximately 7%, but it's also the component that increases the most from average to extreme settings. So we had a low contribution of 0%. The average was actually 0.07%. And I'm saying this because of the value I have here. So when we estimate the relative difference from average to extreme conditions, we see that storm surge is contributing to 10,000 times higher, 10,000 times more than during average conditions. So storm surge is really pushing water levels on the coast on top of a tide that was already there and increasing the elevation of total water levels. In terms of the other components, in orange, the mean sea level is on average 4%, and it doesn't, its spatial variability does not necessarily reflect the local related sea level rise rates. So because in this component, we have all of those other processes I was talking about, sea level anomalies related to climatic oscillations. So we don't have only sea level rise trends. So this is why we don't see this perfect matching contribution of places where sea level rise is higher. In seasonality, while the smallest contributor has a very marked spatial variability, we see its contribution decreases from south to north. And this is directly associated with the Gulf Stream and its variability. It's higher influence on the southeast rather than in the north. Okay. So once again, the larger the tidal range, the larger the tidal contribution to total water levels. And I'm repeating this here to highlight how this is also influences storm surge contribution, and to go back to that point of we don't always have magnitude and relative contribution increasing proportionally. We have different components of setting for the contribution of others. So storm surge contribution, as you can see here, is larger at the mid-north Turner stations, like here in approximately Beaufort, Dock, until Atlantic City, we have a larger storm surge bar, which is related to two main factors. The first is these are the places where we have more influence of tropical and extratropical storm tracks. So we have less influence of extratropical cyclones on the southeast coast, but on the southeast coast, we also have a larger tidal range. So with a larger tidal range, we already have a baseline when the tides are high, where an extreme is more easily achieved because we require a smaller storm surge for this water level to become extreme. So this is why we're seeing a larger contribution of storm surge here, because we have smaller tidal range and we have more extratropical cyclones in these places. So with a smaller tidal range, we require a larger storm surge to make this event more extreme. So this is why we see this larger contribution at these places. We also see larger contributions of wave run-up at these mid-northern stations, which is still associated with the storm systems that occur in the region, but it's also associated with tidal range again, because I'm not showing here, but wave run-up magnitude doesn't vary significantly, the magnitude, because there are subtle variations in wave climate across the US Atlantic coast. We don't see a wave height and a wave period varying as much. It doesn't vary significantly. So the spatial variability of this component may reflect the variability of the other processes that are contributing to still water levels more than the variability on the wave climate. So moving on to the second question. Here we have a plot where in the y-axis we have the currents in percentage of the annual maxima events for tides in purple, storm surge in green, wave run-up in blue, and the annual maximum of storm surge occurring with wave run-up in turquoise. So on average, 61% of all total water level annual maximas occur with the annual maximum wave run-up. So most total water level annual maxima are occurring with the yearly peak of waves, which is also in accordance with the results we just saw, that large contribution of waves to extreme total water levels. Storm surge has a small percentage of occurrence. The annual maximum storm surge does not occur as often with the total water level annual maxima as waves, so only a 21%. But from this 21%, 72% occur with the highest wave run-up of the year, because once again, we have storms influencing both wave climate and causing the storm surge. So both of these components are affected by storm systems. And this is why we typically see the annual maximum storm surge occurring with wave run-up and with total water level annual maxima altogether. Tides annual maxima, they are typically represented by equinoctial spring tides. So this typically occurs during the spring and autumn equinoxes. So there's a very small occurrence of these events, only 3%. You don't even see purple on this plot. And this is because tides do not drive individually an extreme. They need the other components for total water level to become extreme. However, when we assess how many of these total water level annual maxima events are happening during high tide, we have the majority of it occurring during the tidal high. And the other percentage not included here, the events not included here, they are only 13 centimeters on average below the high tide. So this just suggests that we are having a frequent occurrence of total water level annual maximas and high tides, but not necessarily the highest tides of the year. So this is the second part where I fitted the GEV distributions and I was evaluating the return periods. So we have here on the right the average return period for storm surge. So I evaluated all storm surges at each of these stations, estimated the return periods and average, and this is what I'm plotting here. So the average storm surge return period is color-coded and the size of the circles corresponds to variance. And the same thing here for waves. But just notice that the variance is different. It's reflecting the data set that is mapped in each of these figures. So storm surge and the significant wave height, during the annual maximum total water level, they have this 1 to 3 return period, which indicates that this is a very common process. So it's something that's happening frequently. We are not necessarily having the most extreme storm surges causing the total water level annual maxima. They're kind of average because it's a low return period. But we also may notice that these places where you have this 3-year return period, like here in Charleston or Atlantic City, they have a larger variance, which indicates that these places are experiencing rare events when compared to all of the others. And this is maybe why we're seeing a higher return period. We also see that return periods for both processes do not vary as much in space. And we can say that we are seeing the similar event in terms of frequency, causing the annual maximum total water level across all of these stations. Here I'm plotting return periods, but instead I'm plotting the return period for the maximum storm surge at each of these stations, the maximum storm surge that happened during a total water level annual maxima ever. Same thing here, but for significant wave height. And you can see here that we see a larger spatial variability, which is related to what I mentioned before. Some places may experience rarer events than others, like Atlantic City and Charleston again, which show that larger variance. So there are much rarer events occurring at certain places when compared to others. And here for waves, we see a lower spatial variability because once again, this is the dominant driver. And this is the process, the annual maxima wave run-up is typically causing the total water level annual maxima. So when we compare return periods, we may not get a very high return period for this distribution because the most extreme waves are already causing these events. So we don't see a very high return period or a lot of spatial variability in terms of the maxima wave height causing the total water level annual maxima. So to conclude, we go back to the questions and what drives extreme total water levels on the United States. So in short, extreme total water levels are mainly driven by waves and tides. We saw those large bars contributions, a lot of purple and blue contributing to the annual maximum total water level. But storm surge, however, is the forcing that pushes water levels to maximum settings because tides and waves are always important. And we saw that relative difference, we have a 10,000 higher contribution when we compare average to extreme settings. So storm surge is pushing these water levels to cause an extreme event. And waves are also affected by storm systems. So this is why wave run-up contribution is the largest during extreme total water levels. They always matter. And now they are also being influenced by storms. So they will be the component that influences the most. For the second question, are extreme total water levels driven by extreme processes? Not necessarily. So most total water level annual maxima occurred with the annual maxima wave run-up, but the minority occurs simultaneously with the storm surge annual peak. So we still have higher storm surges occurring in a given year, and they're not causing the annual maximum event, but this does not mean that they're not causing an extreme total water level, because in this research, I'm looking at annual maxima events. But if we had the annual maximum storm surge combined with a high tide and the annual maximum wave run-up, we could have seen even worse total water level events with worse consequences in terms of coastal hazards and impacts to coastal communities. So the results herein, they are highlighting that we do not see worst case scenarios occurring frequently across time. And the most important takeaway is the combination rather than the individual extreme itself that has the potential to produce extreme total water levels. We need to think about all of the components and not only focus on one, because global climate change is affecting each one of these components differently. So we need to put all of the puzzles together, the puzzle pieces together, so we can understand what is happening to extreme events on the coast. And with that, I conclude, and I thank you for your time. Okay.
Yeah, the database is running from 1970 to, have you tried to see if the results were different? If you took, like, if you parsed out the database and just took different segments to see if the results have changed dramatically? I'm thinking maybe, something's happening maybe more recently because of climate change coming back in the past. Maybe this, and if you're taking this as one temporal statistical population, you may have several populations where there is a shift or change. It's like, with stuff that's going on with rainfall patterns and climate change, mid-70s, everybody said mid-70s, something shifted. We're starting to see, increases in secular trends, increasing variability post whatever 70. I can't remember the 70s, but anyways. But did you try something maybe like that and to see if the results were consistent? A lot of your results are based on that average, based on what's going on in the time.
So you're talking more about the second part when I'm estimating return periods. Yeah, since I didn't try to do that because I'm looking at annual maximum events, so I only have 40 events.
Oh, yeah.
So that would lead me to have a very short data record. But what I did do is whenever I'm looking at this average related contributions, I do look at each of the years for each of the stations individually because I may get for example, influence of the nodal cycle for tides or something like that. And I want to make sure that I'm capturing all of this variability, understanding what's happening with the data.
You're limited.
Yeah.
Do you think that the results that you have are geographically extendable? Would the Gulf Coast be behaving the same way? Or would the East Coast of China behave the same way because it's...
Probably not. Like I've done some things in the Gulf Coast and you see the storm surge contribution larger. And it also changes for tides because we have diurnal tides on the Gulf, but here we have mostly semi-diurnal. So the patterns are different, but it's replicable though. Good question.
It's maybe a ridiculous question, but it seems like the storm surge and the tidal wave run up. Would there be a way to predict when the storm surge is going to come in? So if the storm comes in at the same time with the tide, that's when you'll have the most.
Yeah,
like that.
We can do predictions about that, and we are actually considering because this is the first part of my research. So I'm trying to move on to the next chapter where I start looking at how this process will vary with different global climate change, different global climate change models and scenarios to see how this will vary and change the related contributions. Because I expect to see some changes if we're changing the frequency of storm surge or the magnitude. How will this affect?
We don't know when it's going to come ashore, so it may come at the same time, like 3 o'clock in the afternoon, or happen to coincide.
Yeah, like
what about short-term forecasting? I think that's what Cynthia is more
Short-term.
trying to get at rather than long-term. Could you calculate a total water level with storm surge predictions and tide predictions?
yes, you can do that. Have two different, use different methods for a shorter term. I was thinking more global and longer term.
Yeah, I was thinking both, but
No, yes, it definitely can do that, especially because tides are deterministic. So we have very good tidal predictions. Yeah, that's the problem.
so some kind of probability.
Yeah. And we're also limited by the length of the records we have. That's also another limitation of the predictions. I see.
Yeah, I guess it was related to that. I don't know. I don't know anything about this. It's a really big question, but I guess it's with the worst case scenarios not happening, but is that happening by chance? Data, or is there essentially a reason they're not happening? How many would you expect would have happened?
That's a very good question. So there could be two things. We may be limited by the length of our time records. Because another thing is the reason why I'm looking at from 1980s until 2020, not going back into the past, is because of the wave data record, which is very hard to get very good wave data. They don't go back as much in time as tide gauges. Like I have tide gauges that have data from the 1930s. So, but we don't have wave data, so we will miss part of the story. But yeah, we do not, I don't think they're very frequently experienced across time because we do not necessarily have all of these components aligning together. It's very hard for them to align perfectly together at the exact same moment to cause the extreme total water level. Like we can have displacements, like we saw that one with the storm surge was still on the same day, but it was just a few hours later, the peak of the storm surge, but that was already causing a lot of impacts. And if we also start thinking about the duration of these events, this will also be impacted by these peaks that, even though they are displaced, they are overlapping because they're happening in the same time window. So they're still having implications not only over magnitude, but over the duration of these flooded events that we're seeing at the coast. So we can say that they are overlapping. Does that answer your question? Okay, thank you.
So, I don't think you said it this way, but I feel like, is it true that we're looking essentially at what is the 1 year return interval for total water level, and what is the contribution of this price to that?
Yeah.
Right? Because I guess so first off, from a communication thing, maybe this is a difference in subdisciplines, but I heard extreme total water level, which you called it a bunch of times. That made me think, what is the record event that's ever occurred? In which case, my mind went straight to hurricanes. And so for a bit, I was confused, thinking like, wait, storm surge should be a huge, much bigger aspect of this. But then when it's 1 year return interval, yeah, it totally changes the context. So I don't know if there's a labeling thing as opposed to the word extreme there that would help in that. The second thing is, I liked when you talked about along the East Coast, there's that middle section that is going to get both tropical and extratropical influences. I wonder if that is a statistical issue of you doing the 1 year return interval thing, or as you talked about it as being explicitly tied to astronomical tides. And this is the part where I don't know as much about the ocean side of things. I do it of the water.
Okay.
But I'm interested to hear if that's actually the case or if it's just a statistical issue.
So I'll start answering your second question. So I did the same analysis for with more extreme events, because here I'm defining extremes as the annual maxima event. So I've done with a peak over threshold approach, and I found pretty much the same pattern spatially, like it doesn't change too much. Like the percentages are very similar across space. So I think that answers the second question. So doing with more events will lead to the same results. For the first one, you're asking about the 1 year return period event. So we are looking at the most extreme events on record. So we are looking at hurricanes, we are looking at this extratropical cyclones, but they are leading to this 1 year return period because they're happening on the annual maximum frequency. They're happening annually. So this is why we're getting that average, because I have storm surges causing some of these events that they have a 7 years return period for the storm surge, but they're still causing the annual maximum event. So that is not the 1 year return period storm surge. Is that clear now?
I think so.
It's a lot of
I think
annual maxima, and I know it gets repetitive.
no, I like the study because I feel like things I've heard studies so far is either on the one hand, what is the increase in so-called nuisance flooding, which is purely tides plus sea level rise, and on the other hand is what is the maximum from just like hurricane stuff. Whereas saying this 1 year return, looking at the parts of all of that, it's like an individual, but still important for decision making.
Yeah. Not to spoil, but we're also interested in looking at the 100-year return period events and look what the relative contribution looks like. It's also on our plans. Caroline.
That was a lovely presentation.
Thank you.
What would you say would be the practical application of your results?
Oh, that's a very good question. So as I was mentioning earlier, we can use all of these predictions. Once we can get this also global climate models projections, we can see how each of these components are changing, and we can use this to plan better for design events and thinking about what will be, they make better predictions in terms of what will be the coastal hazard impacts. Because now we're not looking only at storm surge or sea level rise. We're looking at all together and seeing how they're changing, how they are interacting, because we're looking at the related contribution. So we can apply that for urban and emergency planning. We can apply to design to use as standard for design events and for implementing mitigation strategies on the coast, and especially because here we are focusing on both flooding and erosion hazards. So that would be the application.
I want to know whether I have to lift up all my stuff off my garage
Oh,
floor.
I
which is
think
right
so.
Next to the coast tonight.
Probably.
Probably.
You haven't done that?
I have a question. How much in the extreme events, total water level, the higher they are, as a duration also? Is there consistency in the duration?
That is a
Like,
very
is
good
that
question.
things are above whatever?
I would say that not necessarily. It will also depend on the contribution of the processes. I'm also looking at other thing. I also have some slides. I'm spoiling more things. Let me go here. So, so another thing I'm also doing is I'm looking. So here we have our beach again, and now it's not flooded like the other one. So here we have our dune toe, we have our dune crest. So there are different storm impact scale regimes where we can look at the interaction of these total water levels with beach ecology to understand more about coastal hazards. Because on the previous analysis, I'm focusing on what is driving extreme. Here I can think about some of these implications over the beach and how it will affect erosion and flooding. So we have the swash, which it doesn't cause any coastal hazards. But then we have the regime of collision, where we have the water levels colliding with the dune toe and up to the dune crest. And if we have water going over the dune, we have the overtopping regime. And this is where we have problems. So one of the things we will also be looking. So here I was using a different approach because this is a little bit older. I changed how I look at some of my components. But we can look at how many hours water levels are spending on the collision regime, on this one right here, which is in between. It's kind of intermediate. It's causing impacts, but not as much as overtopping. So I'm interested in seeing how much this is changing over time. So there is a rise in the number of hours water levels are spending over the collision regimes. And we can also see how different processes contribute to each of these regimes. So then we can start thinking about the impacts. And here is just a distribution. You can see across all total water levels on record, how many total water levels over the swash, collision, and overtopping. So we can start thinking about things like that.
Yeah.
Don't you love how she had the slides for you?
Yeah, exactly.
Ciao.
Thank you for your presentation. I really enjoyed it. I had a question about your stations. Because you had 10 stations and then it looked like for Florida, they didn't extend below
Yeah.
Fernandina Beach. So I just was wondering because, and I don't know a lot about tides, but I've seen a lot of king tides show up in the news lately in Miami. So I didn't know if you were planning or if you already had extended your stations down for the Florida coast.
That's a good question. I have two reasons. First is data gaps. So I'm looking for Fernandina up. This is also why I don't have any stations on Maryland. So I have Virginia and then Delaware. And the other reason is right in front of Miami, we have the Bahamas. So the hydrodynamics and the processes there are way different. And I'm trying to focus more on similar stations.
So I was wondering, like, if ocean temperature and salinity has any impact on total water level.
Ocean temperature, yes, it's included on the seasonality component. Salinity, no, I would say no.
Anybody else? Thanksgiving, so everybody enjoy your holiday.